Friends, welcome to my channel. Today's topic is types of functions. First, let me give you the definition of a function. A function from a set A to a set B is a relation where all the elements of the first set are related to a unique element of the second set. It is denoted like this: f from A to B. Here the first set is called the domain of the function and the second set is called the codomain. It can be represented in terms of an arrow diagram, just like that. Consider two sets A and B. Let f be a relation from A to B. Consider two elements x1 and x2 in the domain of the function and two elements y and z in the codomain. In that case, the two elements x1 and x2 can be related to the same element y in the codomain. Here z is left untouched in the codomain. Consider one more relation from the set A to the set B, denoted like this. Here x1 and x2 are two elements in the domain which are related. See how we relate? x1 is related to y and z, which is not permitted in case of a function. Means any two elements or two or more elements of the domain can have the same image in the codomain, but a single element of the domain cannot have more than one image in the codomain. So the first one is correct, but the second one is not correct for a single valued function. Let me proceed with more concept of range. What is a range? The range of a function is the set of values of the functions, or you can say the images of the elements of the domain. You can see here in the first diagram, the elements x1, x2, x3 of the domain are related to two elements y1 and y2. y3 is not in the range, so that y1 and y2 will constitute the range of this function in the first diagram. Similarly, in the second diagram, the range is nothing but y1, y2 and y3, because all the three elements are images of some element of the domain. So the range of the first function is y1, y2, and the range of the second function is y1, y2, y3. Now, types of functions. So first type of function is called one-one function. It is also called injective function. See the definition. A function f from a set x to a set y is defined to be 1, 1 if the images of distinct elements of x under f are distinct. That means for every x1, x2 belongs to x, if fx1 is equal to fx2, that will imply that x1 must be equal to x2. Means if you take any two elements from the domain such that their images, just like fx1 is equal to fx2, are same or equal, then the two elements must also be equal. Otherwise, f is called a many one function. We can give examples here. In the first example, the three elements a, b, c of the domain, which are distinct elements, are related to distinct elements x, y and z in the codomain. Therefore, it is a one-one function. Again, in the second example, the elements 1, 2 and 3, which are distinct, are related to distinct elements x, y, z of the codomain. But in the third example, two elements b and c, which are distinct elements, but they have the same image y. In that case, it is not called 1, 1, but it is called a many one function. The first two are 1, 1 and the third one is a many one function. We may proceed to the next one. It is called an onto function, or it is called surjective. A function f from a set x to a set y is defined to be onto if every element of y is the image of some element of x. Means y is the codomain here, and every element of the codomain must be an image of some element of the domain. You can see, you can consider an element y from the codomain, and for that y there must exist an element x in the domain such that the image of x becomes y. Otherwise it is called an into function. You can have examples like this. In the first two examples you can see the elements, all the elements of the codomain. That is, in the first case it is x, these are x, y, and in the second case these are x, y and z. All are images of some elements of the domain. But in the third case there are three elements in the codomain, x, y and z, but z is not an image of any element of the domain. Therefore the third one is not an onto function. It is called an into function. Okay, one more thing we have to remember, that a function is onto if and only if its range equals to the codomain. If the range, you can see in the third case the range of the function is the set x, y, but codomain is the set x, y and z. Now the next concept is on bijective function. A function f from x to y is defined to be 1, 1 and onto. That is bijective if both 1, 1ness and onto-ness of the properties are satisfied here. You can see in the first case it is an 1, 1 function because distinct elements a, b, c of the domain are related to distinct elements x, y, z of the codomain. So therefore it is a 1, 1 function, but it is not onto. You can see z, w is not the image of any element of the domain. Therefore it is an into function, 1, 1 and into function. In the second case you can see every element of the codomain are related to some elements of the domain. Also all the distinct elements of the domain, those are 1, 2 and 3, are related to distinct elements of the codomain. Therefore it is an 1, 1 onto function. This is called a bijection or bijective function. The third one is not a 1, 1 function because b and c have the same image y, and it is not an onto function because z is not an image of any element of the domain. Therefore it is a many one into function. We can have more examples later. You can see one example of a function defined from the set of natural numbers to the set of natural numbers given by fx equal to 2 x. We have to show that it is 1, 1 but not 1, 2 onto. The solution looks like this. Let x1, x2 belongs to n, means x1, x2 are natural numbers. We consider the domain of the function such that their images are same under f. F x1 equals to f x2. By the definition of the function, in the left hand side fx1 is equal to 2 x1, and in the right hand side fx2 equals to 2 x2. By dividing by 2 on both sides we get x1 equals to x2, which is the sufficient condition for f to be 1, 1 function. Proceed to the next part. We consider the element 1 of the natural numbers. 1 belongs to n. It is taken from the codomain. Then there does not exist any natural number such that whose image becomes 1. You can see under f, if you put fx equal to 2 x and that's equals to 1, then x must be equal to half. You can see x must be half, then only 2 into half equals to 1. Means half is the pre-image of 1, but the domain of the function is the set of natural numbers where half is not there. Therefore 1 will not be the image of any element of the domain. Therefore f will not be an onto function. That's how we show a function is not onto. For the next example, it looks similar to the previous one, because here also fx is equal to twice x, but the function is defined from the set of real numbers to the set of real numbers, unlike natural numbers. Here it has to be shown that it is 1 1 and onto. The solution looks like this. We again consider two elements from the domain. This time the domain is the set of real numbers, and the process is same as earlier. Therefore we can take the images equal, and then it comes out to be x1 equals to x2, means it is the sufficient condition for the oneness of a function. And the next part, for the next part we take y, an element y from the codomain. The codomain is the set of real numbers, such that y is equal to fx. Now what is fx? Fx is given to be twice x, which implies y is equal to twice x, and that will imply that x is equal to y by 2. This is simple calculation. Now you see y is a real number here. Y is a real number, and any real number, if you put on the right hand side of this equation, the last equation, if you put any real number, real value of y, we will get a real value for x. Means for all the elements of the codomain y, all the elements y of the codomain, there exists an element x in the domain, such that y is the image of that x. It is written as y equals to fx. Hence it is an onto function. Consider the next example of a function from the set of real numbers to the set of real numbers defined as fx equal to x square. So you have to show that it is neither 1 1 nor onto. The first one, you consider the function like this, and you take two elements minus 1 and plus 1 from the domain. That means the set of real numbers, such that what is the image, what is the image of minus 1? Here you can see the image of minus 1 is equal to 1, and also the image of 1 is 1. You can see it in the diagram like this. Minus 1 and plus 1 both are having the same image under the function f. Also you can show minus 2 and plus 2 both will have the same image 4 under f. Therefore it is not an 1 1 function. That means we can put examples to show that it is not 1 1. See, in this way we can show that it is not 1 1. Again, for the onto part, let me remind you that a function is onto if and only if its range is equal to its codomain. Here the codomain of the function is the set of real numbers. Now we know that x square is greater than or equal to 0 for all real x. Now the value of x square is nothing but fx. Therefore fx is greater than or equal to 0 for all x belongs to R. Means the range of this function must be from 0 to infinity, or that is non-negative set of non-negative real numbers, which is a proper subset of the codomain R. And that means the range of the function is not equal to the codomain of the function. Hence it is not an onto function. F is not an onto function. A geometrical interpretation can be given like this. Consider the function fx equal to x square whose graphs looks like a parabola. In this way it passes to the origin. Now we are considering two values of x, minus 1 and plus 1, for which the values of y are same, that is plus 1. Also you can see the minus 2 and plus 2 have the same image, that is 4. It shows that the function is not 1 1, it is a many one function. The next function is the modulus function. It is defined from the set of real numbers to the set of real numbers. We need to show that it is neither 1 1 nor on 2. It is actually similar to the other problem given to you. You can see how is it similar. You can see the graph of the modulus function. It entirely lies above the x-axis, and this shows that, for example, for two real numbers minus 1 and plus 1, the values of the function will be same. Therefore, it will not be in 1 1 function. As well as the entire graph is on the above the x-axis. This shows that the range of this function is the set of all non-negative real numbers, while the domain of this function is the set of all real numbers. And since the range of this function is not equal to the codomain, therefore it is not an onto function. Proceed to the next one. A function f is defined from the set of real numbers to the set of real numbers like this. So it is like fx equals to 1 if x is a positive real number. It is equal to minus 1 if x is less than 0, means a negative real number, and equals to 0 if x is equal to 0. And we need to show that it is neither 1 1 nor on 2. In a similar way as earlier, we can show that for all x greater than 0, means for all positive real numbers, we will have the value of the function as 1. That will mean that it is not an 1 1 function. And also the range of this function is the set of only 3 numbers, that is minus 1, 0 and 1. But the codomain is the set of all real numbers. Therefore it is not an onto function, since the range of f is not equal to the codomain. You can see it in the graph. For all values of x which are positive, the value of the function will be equal to 1, and similarly minus 1 for all x less than 0. The next problem is a function defined from the set of real numbers to the set of real numbers as fx equal to 3 minus 4x. We need to check whether it is 1 1 or onto. So for this, given the function is this, we consider two elements x1 and x2 from the domain of the function, that is the set of real numbers, such that fx1 is equal to fx2, and if we put the values of values of x1 in the function, in the definition, we get it like this, and it gives us x1 equals to x2, which shows that it is a 1 1 function. Next, for the onto part, consider an element y from the codomain, which is also the set of real numbers. Now you can see, if we put in place of x, if we put 3 minus y by 4 in the function, the definition is given side by there, it gives us the value of y. That means for every y from the codomain, we get a pre-image, namely 3 minus y by 4 in the domain, such that the image of 3 minus y by 4 is y, and that means that the function f is onto. Now the question is how to find this value, how to find the pre-image. How do we let you know how to do it? Let y equals to fx such that y is equal to 3 minus 4x. 3 minus 4x is the value of the function. It is here the value of y has been expressed as a function of x. Y has been expressed as a function of x, which can be done like this. We can reverse it like this, that is 4x is equal to 3 minus y, or the value of x can be found as 3 minus y by 4. And if we put this value of x in the function, if it gives the value as y, then you are done. The function will be onto. Let a and b be two sets. Now define a function f from the Cartesian product a cross b to b cross a such that fab equals to ba. We need to show that it is a bijective function. For that, given the function in this way, now we have to consider two elements. Now this time the elements will be ordered pairs from the Cartesian product a cross b. Those are a1 b1 and a2 b2, such that their images are same. Means f of a1 b1 must be equal to f of a2 b2. Now if we put the values as defined in the function, we get it like this. But we know that two ordered pairs are equal only when their respective elements are equal, and that will give us that b1 must be equal to b2 and a1 must be equal to a2, and this again gives us a1 b1 is equal to a2 b2, means the ordered pairs are equal, and that shows that this function is an 1-1 function. And for the onto part, what we take an element ba from the codomain, that is the Cartesian product b cross a, and for every ba from the codomain, there exists an element ab in the domain a cross b such that f of ab equals to ba. That is the definition from the definition of the function, and that shows that the function f is an onto function, because for every element ba of the codomain there exists a pre-image ab in the domain, and that shows that it is an onto function, and hence it is a bijection. Again, consider the function f defined from the set of natural numbers to the set of natural numbers in this way. Here fn is defined to be equal to n plus 1 by 2 if n is an odd natural number, and n by 2 if n is an even natural number. So we need to show that. So see whether it is 1-1 or onto. The first part is the function is defined in this way. Now what we can do, we can test it by putting the value of n as 1. Since 1 is an odd natural number, therefore we get the value like that, it equals to 1. And again, if we put n equals to 2, since n is an even natural number, it will again give you the value as 1, and that shows that the images of 1 and 2 both are equal. Therefore it can never be an 1-1 function. It is a many one function actually. It is not 1-1. Again, for the onto part, consider a natural number n from the codomain. So it can be in two ways. The natural number can be an odd number or an even number. Let us first check it for the odd number. Let n be an odd natural number such that it looks like this: n equals to twice r plus 1 for some natural number r. So for every odd natural number twice r plus 1, there exists 4r plus 1 in n such that the image of 4r plus 1 is that twice r plus 1. That means for every odd natural number we have a pre-image like that, a pre-image in the domain. Again, consider that n is an even natural number, just like n equals to twice r for r belongs to n. Now we can see that for every twice r there exists a 4r in n such that the image of 4r is equals to twice r. The pre-image of every even natural number exists in the domain, hence it is an onto function.